Hey, welcome. So this is the ninth lecture. What we're going to be doing today, what I want to show today is just a few more examples of 2D kinematics problems along with some ranking tasks that I wanted to go over. Okay, so let's just jump right into that. Now the first one is one I actually did in the previous lecture. It's the reason I'm redoing this is I realized I did it incorrectly. I misread the problem. So I don't want there to be any confusion. Basically, what I did is I flipped the horizontal and vertical components of the velocity. So you go back and check that out, but I want to redo this problem here. Okay, so as I've previously stated, the first step, if it helps, go ahead and draw a picture. Pictures can be great. If it helps you, sometimes it won't. But the key to this one is knowing that this is in fact a projectile that's been um kicked from the ground. It ends up basically on the same level as it starts with. Now, we're told a couple of different things. We're not told what speed it's kicked with, but we are told the components, which in many ways to do kinematics is more useful. And we're told the horizontal and vertical. Now, last time I said it was 12 in the horizontal. It's actually 16 meters per second in the horizontal and 12 meters per second in the vertical. Um, so the Another important thing is that for A and B, we're looking at the total path. So if we're looking for the speed at which it hits the ground, that's going to be this thing over here at the end. And if we're looking for how long it's in the air, that's also going to be at the end. If we're looking for maximum height, so this is A and B. If we're looking for maximum height, that is the final location for C. So it's important that we're going to have a slightly different problem depending on whether we're doing A or B, or A and B, or C. So for A and B, we're going to set up one table. So A, B. And that is going to, again, I like it to be, you have one column for X, one column for Y, and then you put the 5 kinematics quantities there. So delta X, delta Y, um, V naught X, V final X, A sub X, delta T, and then V naught Y, V final Y, A sub Y, delta T. Now, some of these we can fill in just by virtue of the fact that we know that this is a projectile problem. This will be true for all projectile problems. The thing that's true for all projectile problems is that A sub X will be 0 and A sub Y will be negative G. I'm going to let that be negative 10 meters per second squared, like so. You could do negative 9.8. That's up to you, but I'm gonna leave it like that. Now for this particular one, if the thing ends up at the same height that it started at, so you kick it from the ground, it ends up on the ground, then that's nice because your delta Y is 0. You had 0 vertical change. Now, delta X, we don't know this, okay? Now, it turns out we're not actually asked to find this, but we might be asked to. That would be like a range question. Um, so we'll look into that when we go over some of these other examples. But they actually do break V initial X and V initial Y into components for us, which makes this a little bit more straightforward. The V naught X is going to be 16 because that's the 16 meter per second in the horizontal direction. So 16 meters per second. The V naught Y is going to be 12 meters per second in the vertical direction. Now, another thing we can say is about projectile motion is that because A sub X is 0, your V initial X is always going to equal your V final X because there is no change. If your acceleration is 0, that means your change in velocity is 0. So it's always the same. So whether or not you know the number, that's going to be true. In this case, we do know the number. It's just 16. So that's kind of nice. Now we don't know time. This is actually B. And we don't know V final of Y. Now, we are asked for speed. Now, it turns out that's not V final of Y, but we need V final of Y to get to that. So we'll we'll be finding all of these things. Now, it's helpful to understand there. So if you're in the situation where the projectile ends up at the same height that it started at, there's a nice little trick you can do with v final of y as well. This only works again if it ends up at the same height, but basically what you can do is we could do this equation: v final y squared equals 2a delta y plus v initial y squared. Well, we're looking for v final of y, so we'll leave that alone. And if delta y is 0, and that's the key, delta y has to be 0, then we have 2, it would be a sub y, times negative g times 0, and then plus v naught y squared, okay? And this term goes away. We end up with v final y squared equals v naught y squared. Now, to find v final of y, we take a square root of both sides. Important to remember that you take a plus or minus when you do that. And this, that should be v naught y squared. And that ends up with plus or minus v naught y. Now, the question is, which one do we want? Well, in the problem, basically what we've asked this equation for, the way you can think about it, we've asked this equation to give us our velocity given a certain initial velocity and a displacement of y equals 0. Well, displacement of y equals 0 happens at 2 points, at the start and at the end. So we need to exercise some judgment. Do we want the positive velocity or do we want the negative velocity? Well, the positive velocity is the 12 that happens right at the beginning. So that would be a situation where the beginning and the end were the same and delta t would be 0. But if we want it at the end, then that's going to be where the velocity is negative. So v final of y equals negative v naught. And this is because physically, we want the downward velocity. We know physically that this thing is going back down. So our y component should be negative. Okay. So in that case, it's just negative 12. And you can always say that that's true if the projectile ends up where it started. If it doesn't, then you got a problem. But if it ends up where it started, then it will have the y component will be equal and opposite. Now, what we were asked for in part A is the speed. And it's important to know that basically what we've got, we don't know, we might not know what that is, but we have a velocity vector now. And that is 16, or v final vector, I should say, is 16 because we have our v final of x and negative 12. Well, the speed is actually just going to be the magnitude of that final velocity vector. Okay, so we'd use the Pythagorean theorem. We do 16 squared plus negative 12 squared, take the square root of that. It's going to end up at 16 squared is 256, 12 squared is negative 12 squared, or 12 squared is 144. 256 plus 144 is the square root of 400. Turns out that the magnitude of v final is not 400, is just equal to 20 meters per second. Okay. And then for part B, the time. Well, I think the easiest, there are a number of different ways we could get to time with this, generally with the y column. With the x column, we'd need delta x to get to time, and we don't have that. We could find it, but well, actually, we need to get to time before we could find it. So just easier to do this one. V final y equals a sub y delta t plus v initial y. So that'd be negative 12 equals negative 10 for a sub y. And then delta t is what we're looking for, plus 12. So we're going to end up with negative 24 equals negative 10 delta t. And delta t is just going to be negative 24 over 10, which is 2.40 seconds. Okay, so that is how we would do that one. Now for part C, it's important to know that we're no longer, our final condition is no longer when the ball strikes the ground. If we want the maximum height, our final condition is where the ball reaches maximum height. Now, we talked a bit about this yesterday, but I'll just go through it again. You have x and y. This time, you don't know what your delta x is. You don't know what your delta y is, and it turns out this is what you're looking for. No, our V naught of x is still 16. Our V final of x is still 16. Our A sub x is still 0. Our delta t is new. We don't know what that's going to be. It's going to be different. Now, I'll go through and I can actually show you that it turns out that delta t is just half of the total time of flight. But we'll go through that. Our V initial of y is 12. Now our V final of y is different because we're looking at it at a different spot, but we can actually say this. At the top of the flight, right here at point C, this is where V naught y is equal to 0. And the reason is that's where it basically runs out of upward velocity because the pull is bringing it down, slowing it down. It runs out of upward velocity. And right after that, it's going to start picking up downward velocity. So our V final of y is 0 in that case. Our A sub y is still just -10. And our delta t is something that we're looking for. Now we're not looking for delta x yet, so we're not going to worry about that. But basically what I would do here is I would just use we got the V final y squared plus 2, or sorry, equals 2 A sub y delta y plus V initial y squared. So V final is just 0, so that gives us 0 squared, which is 0. 2 times -10 delta y plus 12 squared. Okay. And from there we can move this over to find delta y. And what you get is you get 12 squared over 2 times 10. And as a reminder, the range formula, or the height formula rather, not the range, the height formula was just V naught y squared over 2g. And that's exactly what we've got here. That's why I've left it alone. That's going to be 144 over 20, which is going to be delta y. I should calculate that. We'll go ahead and do that. 144 divided by 20. That's going to be 7.20 meters. Okay. So that is what we're seeing right there. All right, so that is our height. Now, one of the things we can do is we can actually find our delta t. And this is kind of cool. And we could just do it with the V final equals A sub y delta t plus V initial. And in this time, we just end up with 0 equals -10 delta t plus V, or plus 12. And that's just going to be -12 over -10 equals delta t. So that equals 1.2 seconds, which 1.20 seconds, which notice that's exactly half of what the total flight time was. So this is another thing you can do. If you're looking for the time of maximum height, it's just half of total flight time, which kind of makes sense. It's a symmetrical path. It makes sense that it would take, half as much time to get to its maximum height as it does to come down. So that's something just worth remembering there. The next problem I want to do is actually pretty similar. It is this daredevil problem. And it says a daredevil is attempting to jump his motorcycle over a line of parked buses from a ramp. Okay, so basically what this ramp is saying is you've got this ramp, you've got this biker going at some velocity. We'll make there, that's a biker. And he's going at some velocity in this direction. Now we know this angle is 32 degrees. Now we also know that once he leaves, basically what's going to happen is he's going to basically turn into a projectile. Now the idea here is that we have this long line of buses here. And so the question is asking is how many buses? Now, fundamentally, all that's asking for is it's just asking us for a delta x. The other thing it does tell us is it tells us that the bus height is the same as the ramp height. So basically, the problem effectively ends once he passes below his original height. Either he's made the jump or he hasn't. And it either goes well for him and he makes the landing, or he clips his tire and has a horrible accident. So the point is that we're not looking at buses that were higher, in which case he'd have to be higher than his initial height to clear it, or buses that are lower than the ramp, in which case he would have a little bit more time. So we're looking at buses that are of equal height. Now, basically what we're looking for is we're looking for delta X. Now, it wants us to measure it in buses, measured in buses. And the point is that one bus equals 20 meters. So we'll do this in SI, and then we'll just convert that distance to buses after we get done. Now, this is pretty similar to the last one. The main thing to know here, and I'll fill out the table just to be clear. The delta X, that's what we're looking for. Part B asks it's a little discussion about the error involved. Delta Y, because this thing ends at the same height that it started, delta Y is 0 again. V naught sub X, V final sub X. Well, we do know V final sub X is equal to V naught sub X because A sub X is equal to 0. V naught Y and V final Y. Now, I'm going to take advantage of that thing we just discovered and realize that V final Y is equal to negative V initial of Y. Now, we don't know what our initials are yet. We'll get to those in a minute, but we don't know what they are. And then A sub Y is equal to negative G, which, again, I'm going to let equal negative 10 meters per second. Delta T, we don't know for either one of these. Okay. Now, what we can do here, the point that we have to know is we need some way to get our initial velocities. Okay, we can't really do this without them. We're going to have a lot of information once we get those, but we don't have near enough information yet. So here is the thing. We are given an initial velocity vector. Okay, and we're basically told, okay, your velocity vector looks like this. And the magnitude of this thing is 40.0 meters per second. The angle relative to the ground is 32 degrees. Okay, so that is the angle that you're going to find this at. All right. Now, from here, in order to find your components, what you need to do is you need to do the following. You need to break this into its X and Y components. So you need to realize that you have a V sub X and a V sub Y. Now, V sub X, say V naught sub X and V naught sub Y, is going to be 40 cosine of 32 degrees, and V naught sub Y is going to be 40 sine of 32 degrees. Now, basically, all that's doing is it's manipulating the trig identities for this triangle. But that's basically what you're going to be looking at right there. Now, let me just run through this real quickly. One thing to note, depending on which calculation software you're using, make sure you're in degrees. If you're in radians and you're taking these angle measurements, it will throw you off. Okay, so make sure your calculator is in degrees. This ends up being 33.92 for the X. And then 21.20 for the Y. Okay. And then from there, we're pretty straightforward because we could just say, okay, that's negative 21.20. This is equal to 33.92. And from there, we need to first find the delta T because we'll use the delta T to cross columns, and then we'll find delta X. We can't actually find delta X with the other equations because this acceleration goes to 0. A lot of those equations just become trivial, and we can't actually find the delta X with them, so you need to be careful with that. We need the delta T if we're going to do this. Now, for here, what we're going to do is we're just going to say, okay, I'm going to use this equation, V final Y equals A sub Y delta T plus V initial Y. Now, again, this equation, if we didn't realize this identity, that the V final Y is just equal to the negative of the V initial Y, we wouldn't be able to use this equation. Since we know that, we can use that equation and it works out fine. If you're dealing with something that's different than this, where you're not dealing with a delta Y equals 0, that relation doesn't work. So you got to be careful with that. But in any event, what we end up with here is we just end up with delta t ends up being 2 v naught y. Actually, it's 2v. Yeah, 2 v naught y over. No, it's 2v final y over a. 2v final y over a sub y, which is going to be 2 times negative 21.20 over negative 10, which is going to be 42.4. So delta t is going to be 4.24 seconds. Okay. And then from there, what we can do is we can do delta x equals 1/2 a sub x delta t squared plus v naught x delta t. This thing goes away. And from there, we just get delta x equals v naught x delta t. Now, the reason that first term went away is because a sub x was equal to 0. So irrespective of what delta t squared is, then that entire term just goes to 0. So from there, that's just 33.92 times 4.24. Delta x is then going to equal 33.92 times 4.24, 143.8, or 143, just 143 meters, keeping it to 3 sig figs. Which means that is going to be 7 buses. Now, not a ton of room for clearance there. It doesn't take much loss of speed, like really just a loss of like 1 meter per second in speed, and he would not get the 7 buses. He'd only get 6. And if there were 7 buses to jump, he'd probably clip his back tire and flip over and be going very fast when he hit the ground. And that would be painful, I would imagine. But anyway, this thing jumps 7 buses. So because 1 bus equals 20 meters. All right. So that's something to keep in mind with that. All right. We did do a projectile thrown from a roof last time. Now, one of the things I wanted to talk about is, let's just say, I'll do just a third example. So let's say we've got a ball being thrown off a wall. We'll just make the wall 10 meters. The ball is thrown at 10.0 meters. 15.0 meters per second and it's horizontal. Now, one thing I want to go over is there is a problem in the previous lecture where we go through this, something similar. But one thing that wasn't asked is, what angle does the ball hit the ground with? And I want to go over how we're going to need to do this. All right. So what we could do is we would set up just, delta x, delta y, or sorry, x and y. And then delta x, we don't know what that is, and we're not actually asked to find it, so we'll probably leave that alone. Delta y is going to be equal to negative 10. Now, it's the reason I'm doing negative 10 meters is because it's going down. So I'm letting down be negative, up be positive. Pretty standard, pretty straightforward. V initial x equals 15 meters per second. V initial y, this time because it's horizontal, there is no vertical component. So that's nice. Having zeros does simplify a lot of our equations. V final of x, not y, but x. As a reminder, because a sub x is equal to 0, V final x is just going to be 15 meters per second. We don't know delta t. Don't have enough information to get that. And now V final y. This we don't know. A sub y, this we know, negative g, negative 10 meters per second. Delta t, we don't know this either. Now, it turns out we're not going to need the delta t for this one, because if we want to know what angle the ball hits the ground with, basically what this is information about, this is info about the velocity vector. Okay. Angle that it hits the ground with, basically that's the angle of the velocity vector. And I'll say, relative to the ground. So basically what we're saying is that our V final will look like this. And it will strike the ground with some angle theta. And we need to know that. Now, in order to get that theta, what we're going to need is the x and y components of our velocity. So we're going to need our v sub y and our v sub x. Now, we actually have our v sub x in the v final. It's just 15. But the vy we don't have yet. Because remember, this is final. So we need to find our v final of y. To do that, we're going to apply our kinematics equations here. The time independent one is the one we want. So v final y squared equals 2a delta y plus v naught y squared, or v naught y squared. Now v naught y is again just 0, so that cancels out. And what we end up with is v final y equals plus or minus square root of 2 times negative g times negative 10. So this is going to end up being plus or minus square root of 200. And that's going to be, I think, 14 point something. So 14.1, I think. Yeah, 14.1. So v final of y equals plus or minus 14.1 seconds. Now, or 14.1 meters per second. Now, the idea is which one do we want? Do we want the positive or the negative? Does for the purposes of this problem, it doesn't really matter, but it's worth noting that we want the negative because the ball is going down. Now, when you're asked to find this angle relative to the ground, it's important to know that you're not being asked to measure from the positive x-axis. You're asked to being measured, from the ground, the short angle from the ground that the ball is hitting in. So you got to be careful about what you use here. It's not too bad. All you need to remember is that basically you just want the magnitudes of the sides of the triangle. So even though our 14.1, even though our velocity was negative 14.1, for the purposes of this triangle, this side right here is just 14.1 meters per second. And this side right here is just 15. So that's fine. So what we'd be saying is we'd be saying tan theta equals 14.1 over 15. So our inverse tan of 14.1 over 15 should give us our tangent it should give us our angle in degrees. So change that, and then we'll do 14.1 divided by 15, take an inverse tangent, and that is going to give us 43.2 degrees. Okay. So there are, you could solve for other things. You could solve for the range. That would be for delta x. You could solve for the time of flight. You could solve for the speed. That would be the magnitude of the velocity vector. But we hadn't done the angle before, so this was one thing I wanted to do here. The last thing I want to talk about, I want to show some of these some of these problems from the upcoming assignment, not the one that's due this week, but the one that you'll have to do next week. And basically what I want to do is these are ranking tasks, and I just kind of want to go over a couple of them, or go over one of them as a sort of reminder. So we'll go to this and okay, copy image, and hopefully we can put it in here. All right. So what we have here are shown below are 6 velocity time graphs for toy robots that are traveling along a straight hallway. All graphs have the same time and velocity scales. That's important. We couldn't do this one if we didn't. We're not given the time and velocity scales, but we are told that they're all the same. So they're all measurable, or they're all commensurate. We can compare them. They're comparable. Now, we're asked to rank the magnitude of the displacement. The main takeaway from this one that you need to get is displacement is area under curve. Now, you can make some magnitude judgments, but honestly, I think it's fairly straightforward just to calculate it. So if we look at A, it's basically you can just count the squares. It's five squares. However, note that the velocity is negative, so velocity is less than 0. This means that delta x will be less than 0. So this one has a -5. Now, the fact that that is true, that basically corresponds to this idea that we have area underneath our y-axis instead of area above, or our x-axis instead of area above our x-axis. Okay, so that is -5. So that one is fine, and it's negative. Another negative we have is C, and this is basically going to be 5 is the base, 1.5 is the height, and then it's a triangle, so you have to multiply by 1/2. So it'll be 5 times 1/2 times 1.5, which would be 2.5 times 1.5, which should be 3.75. So this is -3.75. Okay, cool. So those are our two negatives. We look at B. It's basically C flipped, so this is just 3.75. We look at D. It's 5 by 1.5, so that is 7.5, and that's also positive. Now, E is kind of interesting in that what's going on with E is that we're basically getting a half and half here. So what we've got is we've got negative, that looks like this thing right here looks like, so that's -1 times 1/2 times 2.5, it looks like, because 2.5 would be the base, so 2.5 times 0.5, so it'd be -1.25. And then this over here is the same triangle, it's just positive, so this would be plus 1.25 right there. So the total here would be 0. Okay, so, and the way you can think about this is this velocity started out negative, so it started going backwards, but when the velocity got to 0, this is basically the thing stopping and then turning around and going the other way. Now, because these two displacements are equal, it's saying the distance it went back, it went that same distance forward. And you can kind of see that. It's with the areas, the two areas are equal, so that's what's going on with this one. Now here we have a base of 5, a height of 1, triangle, so it's this area right here. 1/2 times 1 times 5 is just 2.5. So now we have numbers for the areas that we can rank. D is the largest at 7.5, then B at 3.75, then F at 2.5, then E, we get to 0, then C is a, E, not O. C is a negative 3.75, and A is an even larger negative. Now, the larger negative is considered the smaller displacement, okay? Because you do view negatives as being more to the left on the number line. That's how it goes, okay? So that's what we're seeing with that one. Now, I wanted to do this a couple more times. I'm actually going to paste this twice, because you could be given the exact same graphs and asked to rank different things. So what I'm going to ask you to rank this time, and we'll change this to orange. This time, instead of displacement, I'm going to do distance. Now, most of these converting from our displacement to distance is fairly straightforward. Distance is just a positive, it's a total length traveled. So if we look at part A, basically this thing was going in the negative direction the whole time. It went -5 in that direction. So now its distance is just going to be +5. Okay. The displacement is identical for B, is identical to its distance, because it only ever goes in the positive direction. It is slowing down, but it's only going to be 3.75. This time for C, instead of -3.75, it's going to be 3.75. We'll drop down to F. That F and D are both, neither of those change, so it's just 7 and 2.5. Now, E is the tricky one that you got to watch out for. because E had zero displacement, but that's not because it had zero distance. It had zero displacement because it went some distance in one direction, then some other distance in another direction. So basically what you're going to have to do is you're going to have to take this. This was a negative 1.25 in displacement. Well, in distance, that is not a negative, it's a positive 1.25. And this one is also a positive 1.25. So the total distance traveled here would be 2.5. Okay. So we've got a oh, I think I might have made a mistake. I think I might have said this was 3. Yeah. In any event, we've got a yeah, I think I might have actually made a mistake in this when I did it in class. So for those of you that are watching from the class, just know that there was a mistake made there. But again, our biggest distance is still D, but then A is our next biggest distance because that was 5. And then B and C are actually equal to one another now. And then so are E and F, as it turns out. They're both equal to one another as well. They're both equal to 2.5, which, that kind of makes sense. That's what's going on there. All right, last one. I want to talk about, instead of displacement, we'll go to blue. This is going to be acceleration. Now, important that you know that acceleration is the slope of the graph. Okay, you can get there pretty readily. You can get there pretty handily if you know that that's what acceleration is. Now, basically, I know that because A is a horizontal line, its acceleration is 0. Because D is a horizontal line, its acceleration is 0. Now, if you look at the rest of them, B is actually, we could figure out what B is, but we don't really need to. And the reason we don't need to is because it's negative. So your acceleration is negative. So it's the only one where it's negative. So we could say from the get-go, B is the least because it's the only one that's negative. And then A and D are equal to one another because they're the only ones with 0 acceleration. And all the other ones have positive. Now we should probably figure out what that is. But the slope, again, is just rise over run. So rise over run. Now, the interesting thing is each one of these have a run of 5. So it'll be nice. All we got to do is figure out the rise. C has a rise of 1.5. E has a rise of 2. And F has a rise of 1. Okay, well, there you go. E has the largest rise, so it has the biggest acceleration. C has the next largest rise at 1.5. And finally, F has the third largest rise at 1. Now, we'd say A and D both have rises of 0, which is why they come after, and B has a negative rise, so which is why it comes dead last. Okay, so that's the explanation behind these things. I'm going to go ahead and cut this explanation there, and we'll end this lesson, and hopefully this gives you what you need to work on the homework that is due next week. Thank you for joining me. I will see you in the next lecture.